In this video, I'm going to introduce the idea of a power series. There's an entire chapter in your textbook devoted to power series. We've been discussing series, whether they were geometric series, P-series, telescoping series, alternating series. We've looked at different kinds of series. But to have one entire chapter devoted to one particular type of series should indicate to you how important power series are. Power series are one of the most powerful tools that we have coming from calculus. They're used every day in the real world in all kinds of different fields, from economics, medicine, to biology, to physics, to chemistry, anything you can think of, business. Power series can be used to approximate other functions that might be difficult to compute. There are other ways that we can use power series as well. We'll only touch on the very beginning of power series, but just keep in mind that this is one of the most incredibly useful tools that we get coming out of all of calculus. They are also somewhat difficult to understand, but I'm going to try to break down what a power series is for you so that you can understand it on a conceptual level. If you understand the concept of what a power series is, it will make it much more easy for you to do the homework and to understand how to apply the tools you're learning about power series to problems you've never seen before. Basically, a power series is based on the geometric series. I emphasize the geometric series over, say, the arithmetic series or some kind of recursive series, because geometric series form the basis for the power series, and power series are probably the most important type that we have at this point in time. Let's look at the screen in front of you and talk about the definitions of what a power series is and what it involves. This video is just an introduction and of course is based on the OpenStax Calculus Textbook Volume 2, Section 6.1. I'm going to break this section into two videos. The first just introducing a power series and looking at the radius and interval of convergence. In the second video for this section, I'm going to take a look at representing various functions with which you're already familiar, but representing them as power series. For example, all the transcendental functions that we know so far, such as sine, cosine, tangent, e to the x, natural log of x, arctangent of x, all of these can be represented as power series. This is what makes power series so, powerful. The reason is that a power series is based on a polynomial, and we know that polynomials are defined everywhere. They're continuous everywhere, they're differentiable everywhere, and they're integrable everywhere. Being able to represent a transcendental function in terms of some kind of infinite polynomial would indeed be incredibly valuable and super easy to code in a computer. This is the power and the purpose of a power series. So what are these power series? First off, when you look at a power series, keep in mind that a power series has a variable in it. The variable I'm talking about here is not the variable that you see in the subscript or the index for the normal sequence or the series. Let me give you an example of a power series. Here's a very simple one written to the right. This is the series from n equals 0 to infinity of, say, x to the n. What I mean by a variable is that the index of summation is this n that we have and have been using in chapter 5, but the variable is the x. In other words, a power series, in a sense, has two variables. The variable for the series itself, the sequence, marking which term in the sequence or series it is, and the variable x, which represents something else. This makes it a power series. You'll also notice that the variable x is being raised to a power and that the power is represented by the index of summation. This is where it gets its name, power series. It is a power of the variable x, hence the name power series. These can be thought of as infinite polynomials because if you were to stretch this out into multiple terms, you would see that it is in fact just like an infinite polynomial. Let me represent that for you now. You'll see that I have inserted the representation of the power series that I wrote up above here in hand, and I typed it out for you here in the center. You can see that this does in some sense represent the idea of an infinite polynomial, one where the terms go forever and ever and ever. Remember that a polynomial must have real coefficients and whole numbers as powers on the variable. By whole numbers, we mean the numbers 0, 1, 2, 3, 4, 5, etc. In other words, the counting numbers plus 0. This does give us this infinite polynomial. We can represent all kinds of functions, any function, as a power series, and this makes them so useful in computing situations. Once we have this, we can think of these as some form of a geometric series, where the base being raised to the power, which would normally be r, is in this case x. We're going to go through now and talk about how to determine when a power series converges and when it diverges. And this will be based on the ideas behind a geometric series. We've looked at these in chapter 5, so this should be familiar to you. Let's move on and look at convergence and the definition. In this case, we have the definition for what a power series is. In the blue box, it reads, a series of the form, the infinite sum from 0 to infinity of c sub n x to the n equals c sub 0 plus c1x plus c2x squared plus so on. The c sub n just represent the coefficient of each term. C sub n would be the coefficient of the nth term. C sub 0 is the coefficient of the 0th term. C sub 5 would be the coefficient of the 5th term. C is just a convenient use since C and coefficient both start with the letter C. This is what we call a power series centered at x equals 0. You can also center a power series at any other finite real number. You can call this A. We typically do use the lowercase letter a to represent the series center. In other words, the center of where the series is based. This would be written in the form of the infinite series from n equals 0 to infinity of c sub n times the binomial x minus its center a raised to the nth power. You can see that on the right-hand side, this leads to a binomial expansion based on powers of the binomial x minus a. Later, we'll actually look at something called a binomial series, which is a type of power series and which carries certain unique characteristics and properties. They're also a very important type of series, and we study them separately. This is what it means to have a power series centered at A, where A is not necessarily 0. If A is 0, of course, then it just reduces to the original form of the power series, which you see at the top. Again, we call this value A the center of the series. Because this is based on a geometric series formula, we know that if the base of the exponential type expression is between the values of -1 and 1, we know it will converge. We proved this in chapter 5. Because we know it converges, provided that it's between -1 and 1, we can say that the power series will also converge if the value of x is between -1 and 1, or the value of x minus a is between -1 and 1. If we don't want to write between -1 and 1, remember that we can use the absolute value notation to represent the same idea. Saying that r, absolute value, is less than 1 is the same thing as saying r is between -1 and 1. With a power series, however, because x is a variable, it is possible now for it to converge when it is equal to 1 or -1. However, this is not guaranteed by the geometric series formula. So we will always, in every single case, have to check both the left endpoint and the right endpoint separately. Let's move on and take a look at the next piece of information. There's a little bit of a subtle understanding in the definition of a power series. In order to make the definition precise, we have a bit of a problem if x is equal to the center A, because that could lead to 0 to the 0th power. For this purpose, and this purpose only, we define in this case that x to the 0 will be 1 and x minus a to the 0 will be 1, even if x is 0 and x is a. Ordinarily, this would lead to the indeterminate 0 to the 0 form. We're going to try to avoid having this occur, since if you know that it is 0, then you probably don't need a series at all. But in this case, we do need to make it clear that we have to have this understanding to have it work. Again, the C sub n simply represent the coefficient of whichever term you're at in the series or the sequence. Let's take a look at the formula for the binomial expansion whenever we have x equal to a. Given that we're going to assume that x minus a to the 0th power will be 1, even if x is equal to a, this formula here on the left is going to simplify to the one in the middle where I've replaced x with a. A minus a is 0, and this is going to give me basically just the first term, c sub 0 plus 0 plus 0 plus 0, because I've defined this here, x minus a to the 0, to be 1, even though it is actually a form of the indeterminate 0 to the 0. In other words, this formula for the power series will converge to a finite number given by the initial coefficient c sub 0 if the variable x is equal to its center. This basically is telling us that every series will converge at its center and will converge to the value of the initial coefficient, c sub 0. Now, of course, if the subscript on the infinite series does not start at 0, then c sub 0 should be replaced whichever one does come first. And in fact, in that case, it may well be that it does not converge to anywhere except 0. Let's take a look at the next piece of information. This is the rule or the theorem for the convergence of a power series. When you're looking at a power series, either in its x minus a form or its x to the n form, it will converge or diverge under three conditions. First, notice and remember that all power series do and always converge at their centers. So every power series has to converge at least one place, and that's at its center. It is possible, however, that that is the only place that the power series converges. This is case I, the very first one. The series converges only at its center and diverges for any other value. This doesn't happen terribly often, but it also can occur, so you need to be aware of it. You can be sure that I'm going to include something like this on the homework and on an exam. The second possibility for convergence of a power series is that it converges for all real numbers. This is the best possible situation. This means it doesn't matter what value I choose for x, I know the power series will converge for all values of x. This is what we hope to find when we convert our transcendental functions like sine and cosine, the exponential and the natural log, into their power series form. We would like to be able to say that no matter what I choose for the variable x, I can represent that transcendental function with this infinite polynomial based on the power series. This will also occur quite often in the homework and again on an exam. The third case is somewhere between the two. It converges for more than just the center, but not for everything. In this case, this means that there is some real number r, strictly positive, so that it will converge provided that it's close enough to the center. By close enough to the center, we mean that the difference between what we plug in for the variable and the center is less than r. The length between those two values is less than r. This is very similar to the epsilon and delta definitions that we used in Calculus 1 for doing the definition of a limit. Again, it's the same idea. How far away from A can you be to guarantee that the power series will converge? R. Don't get any further away from A than R, then you'll be safe and everything in between will converge. It will diverge if you get too far away. In other words, your distance from A is bigger than R, then it will diverge. The difficulty with the power series in comparison to the geometric series is that we no longer know what will happen right at R, what happens at the two endpoints of that interval. In a geometric series, it would diverge, but in a power series, because the base of the exponential is x, which is no longer a constant, r, but is now a variable itself, it is possible it could converge. Unfortunately for us, it could converge at the left endpoint, but not the right, or at the right endpoint, but not the left, or it could converge at both endpoints, or it could not converge at either endpoint. That means that we have to check both left and right endpoint on every single power series to know whether or not it converges at the endpoint. There's no shortcut and no way to get around this. Let's move on and look at the next piece of information. In this picture here, you'll see that I've drawn an image of what it means to have an interval and radius of convergence. I also put over here on the right an image of a circle with the radius mark. The idea behind the radius of convergence and the interval of convergence for a power series is very similar to the idea of the radius of a circle. Remember that the definition of the radius of the circle is from the center of the circle to the edge. It is half of the width of the circle, half the diameter. In a sense, the interval of convergence, which represents the whole thing, is sort of like the diameter of the circle from one far side to the other far side. Notice that A, the center of the power series, is in the dead center of the interval of convergence, just like the center of the circle is in the center of the diameter. The radius of convergence, on the other hand, extends from A to one side of the interval of convergence, or from A to the other side of the interval of convergence. This is similar to what it does on the circle, from the center to one edge, but not all the way across. In other words, you can think of the radius here as the length r being the radius of this interval. We don't really know whether these should be rounded endpoints or whether they should be included. These are the values we will have to check. You will know what the endpoint values are because you will take the center and add the radius of convergence to it. That gives you the right endpoint. Take the center, subtract the radius of convergence. That gives you the left endpoint. You'll have to check the convergence of each endpoint separately. Notice that if the center is the only place that the series converges, then this becomes a single point interval. In that case, we can write the interval of convergence as simply A between curved brackets, or you can use rounded parentheses with A to A, or you could also use closed parentheses. They all mean the same thing. In this case, we define the radius of convergence to be 0 or to have length 0 because it doesn't have any width. There's only one number inside of it, so there is no length, if you will. Let's move on to the next piece of information. On the blue box in the screen, you'll see the formal definition for what it means to have an interval and radius of convergence. we call the set of real numbers x where the series converges, we call that the interval of convergence. This is going to be some kind of interval, closed on one end, closed on both ends, open on both ends. It could simply be a single point interval consisting of only the center. If the value is greater than 0, then we know that the r will be greater than 0. R is called the radius of convergence. This is basically the definition for the interval and radius of convergence. If the series converges for all real numbers x, which of course is our absolute ideal situation, then we will say that the radius of convergence r is equal to infinity. In that case, we can say that the interval of convergence is from negative infinity to positive infinity. Let's take a look at one last figure from the textbook and make sure that you understand conceptually what it means to have a radius and interval of convergence. The book did a pretty good job of illustrating them. Unfortunately, they didn't label the situations. This is a problem. So, in the first situation up here at the top, this is the case where the power series converges only at the center or only at the single value a. In this case, the radius of convergence must be equal to 0 because it has 0 length. This means it's only converging here at this one point a, and it diverges for all other values of x. In the second situation here, it converges for all real numbers. In this case, we would write that the radius of convergence is infinity, infinity to the right and infinity to the left. The interval of convergence in this case would extend from negative infinity to infinity, whereas in the first case, the interval of convergence is the single point a. The third case is a little bit more difficult, but what we will typically see in the homework. In this case, it converges for some values of x, but not all. There will be some real number r greater than 0, and if you're between a plus r and a minus r, it will definitely converge. The problem is we don't know what happens right at a plus r and a minus r. The book did not make clear that it could be any one of these 4 possibilities, that it doesn't converge at either endpoint, so it is an open interval of convergence, or it is closed on the left endpoint but open on the right, or it is closed at both endpoints or open on the left and closed on the right. It could be any of these 4 possibilities. In this case, we say that the radius of convergence, of course, is just the value of r, and the interval of convergence will be one of these 4 possibilities. We're now ready to do some examples. In example 1, you see the infinite series from n equals 0 to infinity of negative 1 to the n times x to the n divided by 5 to the n. To find the interval and radius of convergence for a power series, we typically apply the ratio test. On occasion, we apply the root test, but I would say that most of the time it's the ratio test. However, the ratio and root test are the basic ones that we do use to prove convergence. In this case, what we're going to do is we need to rewrite this power series here in its geometric series format. Remember that the form of a geometric series basically looks like the sum from n equal whatever to infinity of r to the nth power, and there may be some coefficient here as well. This coefficient could be a constant anywhere from 5 to pi to e to the square root of 11. However, the basic form for a geometric is something that looks like an exponential. It is a base, which in this case is r, and it is being raised to a power which corresponds to the index of summation. When we look at our example, we do not have something that looks exactly like this. So step one is to rewrite this in a format so that we have one thing as the base being raised to a power. So my first step then is to rewrite this example and to pull the -1, the x, and the 5 together, all being raised to the nth power. If one of these was raised to something like an n+1, I may have to pull off an extra 5 to make sure that all the powers are precisely n. I'll show you an example of that in just a moment. So first I rewrite this one from n equals 0 to infinity, and I'm going to write -x divided by 5, all being raised to the nth power. Now it has the same format as a regular geometric series. The base in this case is r, the base here is -x divided by 5. Since it's raised to the nth power, I know that this must converge and have a finite sum, provided that -x divided by 5 is between -1 and 1. This is step one to finding the interval of convergence. So the next thing we're going to write is we're going to write that down. We have here the sum from n equals 0 to infinity of -x divided by 5 to the nth. To find the interval and radius of convergence, take that base being raised to the nth power, put it in absolute value, and say the absolute value of that thing has to be less than 1. Because it's an absolute value, you can ignore the negative. Basically, what we're saying is this thing must be between -1 and 1. In this case, this basically implies that we have to have the absolute value of x divided by 5 less than 1, dropping the negative since it's in the absolute value. Reinterpreting this, this means that we have x divided by 5 less than 1, but greater than -1. This is just the normal rule for the convergence of a geometric series, where the value of r is a strictly proper fraction between -1 and 1. In this case, since the 5 is now positive, I can multiply all three parts by 5, and that will lead to the next inequality. In the next line, you'll see that I now have that x has to be between -5 and 5. If it's between -5 and 5, it will converge. This gives me the first indications of what my interval of convergence is going to be. My interval of convergence will be between -5 and 5. However, I don't yet know whether to include -5 or 5. To find that out, we have to test the endpoints -5 and 5. However, at this point, I can tell you exactly what the radius of convergence has to be. In this case, between -5 and 5, I know this has to be an interval that is 10 wide. Take the 10 and divide by 2. This means that my radius of convergence is 5. That radius of convergence is the italicized uppercase letter R. We would write that R is 5. Now let's determine whether or not to include the endpoints in the interval of convergence. Remember what our series looked like after we had rewritten it. To determine whether or not the endpoints are included in the interval of convergence, I need to replace the x with the two endpoints one at a time. So first I'm going to check -5. This is the left endpoint of the interval of convergence. I'm going to take the -5 and I'm going to plug it in place of the variable x. This means that my summation would now look like negative times something divided by 5, all raised to the nth, and I would replace this with -5. When I replace it with -5, this leads to the summation, and again, my lower index goes from 0 to infinity of 5 divided by 5, since a double negative gives me a positive, to the nth power. However, 5 divided by 5 is the number 1, and this tells me that if I plug that in, I basically have the infinite series from 0 to infinity of 1 to the n. This means I have 1 plus 1 plus 1 plus dot 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 forever and ever and ever. This is clearly going to diverge. What would happen if I plugged in the right endpoint? If I check the right endpoint, which is at 5, I will see that I get something somewhat similar. So now I'm going to check the right endpoint. The right endpoint is x equals 5. Plugging this into my summation, I have negative times something divided by 5 raised to the nth power. I replace the variable x with the right endpoint 5, and this leads to the summation from n equals 0 to infinity of, well, negative 1 to the n. This leads to the series of numbers 1 minus 1 plus 1 minus 1 plus 1 minus, and so on. We know from what we did before that in this case, the sequence that is consisting of 1, negative 1, 1, negative 1 does not go to 0, since the even terms go to 1 and the odd terms go to negative 1, and they don't agree. Because they don't agree, the divergence test tells us, since the sequence doesn't go to 0, it's not possible for the series to converge. In this case, then, we can also conclude that it diverges at that endpoint. Therefore, my interval of convergence, or I, is going to be written from negative 5 to 5, open on both ends. What is the center of this interval of convergence? Well, if you're having trouble determining exactly what the center is, notice that the center is, yep, it is the center of the interval. The number that's halfway between negative 5 and 5, yeah, that's 0. The center of this power series is 0. You can also tell by looking at the original form. When I have it rewritten, notice that there is no binomial with x on the inside. Therefore, the center is obviously 0. Let's take a look at another example. Let's take a look at example 2. Example 2 does not look like a power series at first, but if you notice, it does have the variable x on the inside, and it is being raised to a power which involves the subscript n. Let's see if we can manipulate the different factors inside the summand and get it into a more geometric series type form. The first thing I'm going to do is pull the 3, which is on the outside, inside the summand. Because the base of this and this factor here are both 3, I can add their powers. Notice that the negative is not a part of the base being raised to the nth power, otherwise it would be inside parentheses. This will let me rewrite it in the following format. This gives me the sum from n equals 0 to infinity of a negative 1 times 3 to the n plus 1 times x to the n plus 1 divided by n plus 1. I can then pull the 3x together into the same base since they have the same power, and this will let me rewrite it into this form, with the negative 1 separated from the other factors. 3x being raised to the n plus 1 divided by the n plus 1 power. Now the problem with this is it doesn't look exactly like a geometric. In a geometric, my r is being raised to the nth power, but here I have the n plus first power. This is easy enough to fix. If I want to back this up 1 and make this power n, I need to push the subscript forward by 1 and make it 1. That means that I can rewrite this in this form, n equal 1 to infinity, negative 1 times 3x, now raised to the nth power, divided by n. This is a power series, again because I have the variable x involved being raised to a power which corresponds to the index of summation. The difficulty with this particular series is that it is not in geometric form, and there's no way to make it be in geometric form. Remember that geometric form is based on the exponential. In other words, we typically have some r being raised to some power based on the index of summation. However, we have this divided by n here, which is not being raised to the nth power. There's no way to rewrite this in a strictly geometric series format. This is when we need to use the ratio test or the root test in order to determine where it will converge depending on the value of x. In this case, what we're going to do is we're going to replace this here and we're going to find the limit as n goes to infinity of the absolute value of a n plus 1 divided by a sub n. In other words, we're going to apply the ratio test. So now we're going to take the ratio test and apply it to this to see if I can get some kind of limitation on the variable x that will tell me when it will converge and when it will not. Most of the time it is the ratio test. On a few rare occasions, the root test is more applicable, but it's usually the ratio test. In this case, we can think of the -1 as a constant and pull it all the way out of the summation. It is not going to affect the convergence of this series because it is a constant. We can think of this then as simply -1 times the series of 3x raised to the nth power divided by n. We're going to look at this second part here, and we're going to put it into our format. This second part will tell us what we have. When we put it into the ratio test, remember we need to take the ratio of the a sub n plus first term over the a sub nth term. Applying this here, we have the limit as n goes to infinity of the absolute value of quantity 3x to the n plus 1 divided by n plus 1, all divided by the quantity 3x to the nth power divided by n. When we simplify this, we will get the following. By taking the denominator fraction and multiplying by its reciprocal, we can algebraically simplify this complex fraction into a more usable form. This gives us 3x to the n plus first power over n plus 1 times n over quantity 3x to the nth power. Looking at this format, I can see that if I could get the powers to be the same, I could do some cancellation. I cannot cancel the n and the n plus 1 because n plus 1 is a binomial factor group. The whole thing goes or none of it goes. Since this has a higher power of n plus 1, I will rewrite that factor in terms of 3x to the nth power by pulling one of the 3x's off. This will give me quantity 3x, the one pulled away, times 3x to the n. Since the power here is an understood 1 right here above the 3x, I could add the n and the 1 to come up again with the n plus 1. This still is divided by the quantity n plus 1 and still multiplied by n divided by quantity 3x to the n. At this point, though, I do have two factors that match, the 3x to the n and the 3x to the n. Those will cancel, and that will give me a simple and more simplified expression inside the absolute values. Rewriting with what I have left, I have 3x times n divided by n plus 1. The surprising thing is that as far as the limit is concerned, the x is not a variable. It is for us, but not for the limit. The limit considers only n to be the variable, since it is what is approaching infinity. Therefore, I can take the 3x and factor it out of the limit. This gives me 3x, still an absolute value because I don't know about the value of x yet, times the limit as n goes to infinity of the absolute value of n over n plus 1. I know that n and n plus 1 are both positive, so I could drop these absolute values. You can also use multiple examples to come up with the value for that limit, but you should recognize by now and just be able to write down that it goes to 1. This means that the value of the limit is now the absolute value of 3x. Since we applied the ratio test will converge provided this is less than 1. This gives us our condition for the convergence of this series. This is very similar to what we have for the geometric series. In this case, we simply take the 3x and we put it between -1 and 1. This is exactly like what we would do with the geometric form. Dividing by the positive 3 gives us that x has to be between -1/3 and +1/3. To evaluate the rest of it, I need to plug in the -1/3 and the 1/3 into the original series to see whether or not it converges at the endpoints. Let's remember what the original series was. Our rewritten series is here on the left with the -1 still pulled out front. Let's check the left endpoint, which is -1/3. Checking the left endpoint of -1/3 and replacing the x inside of the series with the -1/3, I get -1 on the outside, summation, inside 3 times -1/3 replacing x, all raised to the nth power divided by n. In this case, when I simplify this, I will end up with still a -1 on the outside, summation, 3 times -1/3 is -1, and this gives me -1 to the nth power divided by n. What does this give us? This is the alternating harmonic series. We know from the previous section that this is a convergent series. Because this converges, this means that we will include -1/3 in the interval of convergence. Now let's plug in the second one, which is the value of +1/3. We'll take the 1/3 and again replace the x in our original series with that and see what we get. As you might imagine, this is going to lead to a different result. In this case, we are going to end up with the following. Note that this gives us the harmonic series, since 1 to any finite power is always 1. This just gives us -1 times 1 over n, the divergent harmonic. This tells us that we cannot include the right endpoint. Thus, when we are looking at our results, our interval of convergence should be closed -1/3 to open 1/3, and our radius of convergence is 1/3. The center is, of course, right smack in the middle of the interval of convergence, which is 0. Let's take a look at another example. In this particular example, we do not have the presence of a clearly geometric form. We will not be able to get that because of the factorial. In order to determine whether or not we can use the idea of a power series, which it clearly must be since we have the variable x involved raised to a power corresponding to the index of summation, we will need to use the ratio test. So first we will use the ratio test to determine where it will converge. Let's apply the ratio test. Remember that the ratio test takes the limit as n goes to infinity of the absolute value of the n plus first term divided by the nth term. Let's apply that to our particular sum end here. This gives us the limit as n goes to infinity of the absolute value. Now we will replace each of the n's in here with n plus 1. So this gives us n plus 1 to the 20th power times x to the n plus 1 divided by 2 times n plus 1, close that, plus 1, all in parentheses with the factorial outside, divided by, and now we need the nth term, and the nth term will correspond to n to the 20th, x to the nth, divided by 2n plus 1 quantity factorial. All of this in absolute values. In order to do the division, we'll take the denominator fraction and take its reciprocal and multiply by it. Let's rewrite that now. Go ahead and pause the video and work out the algebra yourself, then turn the video back on and check to see if you have what I have. You'll see at the bottom that I have rewritten the original limit by taking the denominator fraction and multiplying by the reciprocal here. The next step I need to take is to rewrite the 2n plus 3 factorial in such a way that I can cancel with the 2n plus 1 factorial. You'll notice that I also took the x to the n plus 1 from the numerator and split it into x times x to the n. Because the bases are the same, we would add the powers, and 1 plus n is the same as n plus 1. Scrolling down to the next line, you can see that I was able to then cancel the, let's see, what did I cancel? I canceled the x to the n with the x to the n. That left me the n plus 1 to the 20th, the monomial x factor, and the 2n plus 1. I rewrote the 2n plus 3 factorial with 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. In the next line, I'm able to cancel the 2n plus 1 factorials. This leaves me with this expression here. At this point, it would be helpful to split this into two separate fractions so that we can evaluate the limits separately. Remember that the limit of a product is the product of a limit, even though that's not true for derivatives or integrals. Let's take a look at the next steps in detail. It is allowed to split up limits among factors. This lets me split it between the two that are being raised to the 20th power so that I can combine them into one single fraction raised to the 20th power. This is advantageous because I can also pull the limit inside the power. In the next line down, you'll see that I've pulled the limit inside and the 20th power is happening afterwards. Because I have that, I can actually then look at this and think of this as having the indeterminate form infinity over infinity, and I can apply L'Hopital's rule to this step. The derivative of n plus 1 will be 1. The derivative of n will also be 1, which means that this becomes a 1 raised to the 20th power. This is going to give me the constant 1 for that first factor. Now let's take a look at the other factors and see what happened to them. Scrolling back up, you'll see that I split off the factors to the 20th, and that left the monomial x and the two binomial factors of 2n plus 3 and 2n plus 2. The x is actually, as far as the limit is concerned, constant. It's not a constant, but the limit thinks it's a constant, because the limit only cares about n. That means I can factor the x out of the limit. It can pass beyond the limit. In the next line, you'll see that I've pulled it out and it's now in between the two limits. It is still a factor, still being multiplied by the other things. You'll notice I've also dropped the absolute values. Since the value of n begins at 1, we know it cannot possibly be negative. So the absolute values are not necessary. It's not wrong to leave them, but they're not needed. At this point, you should know that the limit of this one is clearly and definitely going to go to 0. What is that going to do to our result? Coming down further, this means that we still had x here, and we now have 0 here, which basically means that we have 1 times x times 0, but any finite amount times 0 does give us 0. This tells us that because the limit does not depend on any value of x, that it will converge. Remember, the rule for the ratio test is that the number you get must be strictly less than 1. Since 0 is less than 1, it converges. Because the x has disappeared from the value, it is no longer dependent on x. This means it converges for all x values. This means that our interval of convergence is going to be negative infinity to infinity, and our radius of convergence is going to be infinity. Let's take a look at one more before we end this video. In example 4, you'll notice that I've left off the lower index of summation and the upper index of summation. At this point, we've been doing series for so long that you should understand that it is, in fact, and should be there, but we can sometimes abuse the notation and leave it off just for ease of writing, since we have to write these so often over and over again. As long as you have it on the initial problem and on the one at the end, I am okay with you leaving it off at the ones in the middle. However, note that it should be there at some point at the beginning and at the end. I'm going to go ahead and write it in just so you remember when you look back at your notes that it should be there. Hold on while I scroll back up to where it should be. My page is going a little wonky. This should be from n equals 0 to infinity, or 1 to infinity. This one is kind of a fun little problem for the simple reason that while it's not terribly difficult once you get it in the right form, the problem is it's definitely not in the right form. The problem is that the powers do not match. One of them is n minus 1, and one of them is 2n plus 1. What can we do to affect this so that we can get something where we can decide whether or not it's going to converge? In this case, it would be almost impossible to get the powers to be exactly the same through any kind of algebraic manipulation. So I'm not even going to try. Because of that, that directs me towards using the ratio test. If I can't easily get it into the geometric series format, then I'm going to have to take it and rewrite it so that I can get it in a ratio format or the root test format. I'm going to choose the ratio test almost all the time, only the root test when the ratio test doesn't seem applicable. So in this case, I'm going to apply the ratio test and see if I can get some kind of condition on x to get it to converge. Remember that the ratio test is going to require us to find the limit as n goes to infinity of the absolute value of the n plus first term divided by the nth term. Let's take a look now and see how we can apply this. You may want to pause the video and apply the ratio test yourself and then turn the video back on to see if your answer matches mine. Looking at this, what I have now is the ratio of the n plus first term to the nth term. I rewrote it by multiplying by the reciprocal of the nth term. You'll notice that the powers are not identical. Since 2n plus 3 is larger than 2n plus 1, I'll rewrite the 2n plus 3 in a 2n plus 1 form. Since it's exactly 2 more than 2n plus 1, I pull the 2 off and write it as x squared times x to the 2n plus 1. Note that 2 plus 2n plus 1 is 2n plus 3, so they are equivalent. Again, comparing the 3 to the n minus 1 and 3 to the n, the 3 to the n is bigger, so I'll rewrite it in the 3 to the n minus 1 form. This means that I have to pull a 3 off. This is 3 to the first, and 1 plus n minus 1 gives me back 3 to the n. This will let me cancel some of these powers. Namely, I can cancel the 3 to the n minus 1s and the x to the 2n plus 1s. When I'm done then, this leads me to the limit as n goes to infinity of x squared over 3. Using the ratio test, I know that this will converge provided that it is less than 1. This gives me the inequality I need to decide where it converges. Again, this is when we use the ratio test to find the interval and the radius of convergence, as opposed to writing it in a geometric form. This leads to the following. The absolute value of x squared over 3 less than 1 can be rewritten without the absolute values as x squared over 3 between -1 and 1. Multiplying all three parts of the inequality by positive 3 does not reverse the sense of the inequality. Now I need to take the square root. However, I have a problem because on the left end, you will notice that I have -3, and I know I can't take a square root of a negative. What this does is provide sort of a restriction on the value that we've got. What would it be had I not taken the absolute values away? What would it look like in its absolute value form? It would look like x squared in absolute value less than 3. Now I can take the square root of both sides, and this would tell me that basically the absolute value of x must be less than the square root of a positive 3. Now I can take it back out of the absolute value format and write it without the absolute values as x being between the negative square root of 3 and the positive square root of 3. In order to determine whether it converges or diverges at the endpoints, I will need to plug them into the original. Let's check the left endpoint, the negative square root of 3. You'll note that I've chosen to leave off the lower index of summation and the upper just for ease of writing. Remember that this replaces only the variable x in the original series. This is going to then be rewritten in this format. I'm replacing it with negative the square root of 3. When I'm looking at this, how can I evaluate it? How can I determine what it is? The easiest thing to do is to rewrite the square root in terms of the 1/2 power. This is going to give us instead negative times 3 to the 1/2 power, and remember that the negative is not part of the base, raised to the 2n plus 1, all divided by 3 to the n minus 1. In this case, the -1 is separate. The -1 is also being raised to the 2n plus 1 power. In this case, I can separate the two and rewrite it in the following format. This would be -1 to the 2n plus 1 times 3 to the, well, I need to distribute the power, 1/2 times 2n and 1/2 times 1 would give me n plus 1/2. However, it's also divided by another power of 3, 3 to the n minus 1. Using the rules for exponents, this gives us the base 3 to the power n plus 1/2 minus, in parentheses, n minus 1. N plus 1/2 minus the quantity n minus 1 would give us 1/2 plus 1, or 3 to the 3/2. Rewriting again, I get -1 to the 2n plus 1 times 3, and again note the n's will cancel, and I get 3 to the 3/2. This is going to be a problem because this is going to give me a value that repeats over and over again. I know that this is going to diverge. You could use the divergence test to claim that the sequence corresponding to the sum end does not go to 0, and therefore the infinite series must diverge. Similarly, if I plug in the upper end, I will find exactly the same thing, but without the -1 being raised to the power. Thus, it will diverge at both endpoints. This gives us an interval of convergence equal to the open negative square root of 3 to open square root of 3. It also gives us a radius of convergence of the square root of 3, and again, our center is 0. This concludes this video, which is an introduction to power series. In the next video, we'll look at some where the center is not 0, and we'll look at how to represent different functions as power series.